or is it QC? I don't know. Reputation.
Okay, so today, let's see. For lecture, we're going to talk a little bit about optimization. So we're kind of wrapping up sort of unit number 1 in this class. I guess we have wrapped up. You guys have now taken your exam and stuff on the modeling and the simulation portion of the class. So that basically teaches us how to think about DERs, how to model them with equations, and then how to put those equations into a computer and get some idea about how the system might evolve over time. So the second unit of the class is more about decision making. So it's about once you have those models, what can you do with them in order to get some kind of useful and actionable information? Like, for example, how big a solar array it should be, or what direction it should be oriented in, or how to charge or discharge a battery. So we'll talk a lot about that in the second kind of half of the class here. And then so that lectures will shift and we'll go back to sort of in eating your vegetables kind of couple of lectures, vegetables kind of lectures. And there'll be some math for 2 or 3 lectures here. And then we'll get more into examples related to DER sort of operation and eventually sizing and stuff like that. But even those they'll have a fairly mathy flavor. And I think that's sort of inevitable because optimization kind of inherently uses math to kind of make decisions. So yeah, that'll be the flavor, I guess, of the second half. And then the homework flavor, basically, you guys have more or less finished your homework. I think probably we will have 1 more problem set, maybe 2, but likely just 1 before the end of the semester. And the idea is that you guys sort of shift from working mainly on homework during the weeks to working mainly on your projects. So, take this week, recover a little bit, take spring break, chill out. Like, breaks should be breaks. So hopefully you don't have to work too hard in this class over break. I won't assign anything. But when we come back from spring break, you guys should be working hard and continuously on your projects. And so you should be getting together with your team members. You should be meeting sort of at least weekly, assign tasks and figure out who's going to do what, and, keep each other accountable for progress toward those goals and so forth. And if you get stuck, if you kind of need some direction, you can always come into office hours and talk with Madar, our TA. You can also come to my office hours and talk with me. And we'll probably have, I think, at least 1 class I have sketched out to have kind of more or less instead of lecture, we will just do kind of a discussion. I don't know what the format will be. We might all just join a Zoom call. And if people have questions, you can sort of just drop in and ask them, something like that. But anyway, that's kind of the flow for the next roughly month and a half, and then you'll be doing your final project presentations there. Okay, so I just wanted to talk about the midterm very briefly. So for the folks in the room, let's see, show of hands, who thought the midterm was kind of an appropriate level of difficulty and time? And then who thought it was like, honestly, this was probably too hard or too time intensive? And who thought this was like, it's too easy?
What were you going for?
You raised your hand for all 3, so I don't think that's all.
Yeah. It's like, what were you trying to go for as far as time wise?
Okay. Yeah, so my target.
The test. Yeah, I think it was supposed to 5 or 6, 7. Yeah.
2 of those 5 hours of figuring out 4.
Yeah.
Never done.
Yeah.
That.
Yeah.
So it was.
Okay, so I'm just going to be transparent here. So first of all, this is only my second time teaching the class. And the first time I did not give an exam, basically because I was like frantically scrambling to put together lecture materials and I just didn't have time to do it. My overarching goal for this midterm was basically to give you guys an incentive to go back and look through the homework again and kind of revisit and relearn things that might not have landed fully the first time. Okay, so I wanted to kind of put something on your calendars to kind of encourage you to do that. And so if you did that, then I consider the exam roughly successful. Now, in terms of what we were going for, like for the details of the exam, I was aiming for, if you had been keeping up with the homework and you felt comfortable with the material, about 3 hours of exam time. There was a problem on there that was almost verbatim from the homework. There were a few things that were changed, and that's a pretty substantial problem. So if you had done that and you were confident in your solution, you more or less copy pasted. You could change a few numbers and make a graph instead of a table or whatever, but basically copy paste. And then the first problem was intended to be sort of at a low level of difficulty and doable fairly easily with the same ideas you had used on homework problems, but in a kind of a different setting. And then let's see, there was the EV problem about carbon intensity and stuff like that, which had a little bit of a wrinkle, but more or less it was algebraic equations that you guys had worked with before.
My only right was that the third question where we had those, boxes with the arrows, we had done that on homework 5, but the problem was when we talked in class on the prior Thursday and did the Q&A, homework 5 hadn't been graded yet. And so when I went back during the exam and looked at that past homework, I saw that I had done something wrong. And I didn't know it at the time when I could ask questions, and then it was kind of too late to ask a question. And the feedback, because it's kind of vague, since you don't want to, give an answer key, I just wasn't sure exactly what to do. And so that was a little bit of a wrinkle, but, I think I was able to figure it out because I went back hopefully, but, we'll see.
Yeah. So the boxes and the arrows and the natural gas heating versus electric heating, I think that was a callback to homework 2, I believe.
Okay.
So that's where that problem, but there was a homework 5 problem that
Yes.
looked similar. It had
Okay.
also boxes and arrows, but
Yes,
about solar
right.
versus
Yeah,
about
sure, not
heat pumps. It's fine. I mean,
No,
I'm
it
sure
worked
you
out.
worked out, right? But yeah, anyway, so there are details like that. But anyway, that was our target was about 3 hours. I think we probably went a little bit over. And I should say, again, just for transparency here, so the instructions on the exam, I think everybody read, they were pretty clear at the top, and they said use only the course materials, your own solutions from homeworks and things like that. After looking at some solutions, it is very clear that some people went a little bit beyond the allowed materials, right? I'm not going to single anybody out, but it was pretty clear that some people had used ChatGPT or other Gen AI kind of tools. And that was technically against the rules in the exam or whatever, but we totally expected it. And probably next time I give an exam like this, where we're trying to facilitate sort of distance learning as well as in-person learning and we do a take-home thing, probably we'll just make that legal. We'll just make it allowed. And actually, problem number 4 on the exam, so we sort of anticipated this and we ran the solutions or the exam through a couple of Gen AI tools, generative AI tools. And I think most of the tools got somewhere between a B and a C on the exam. And problem 4 in particular was a challenge for basically all of the tools that we tried. So if you uncritically basically copied and pasted an AI solution for that problem number 4 or for some of the other parts of other problems, you should expect to get some points off. And it's not strictly because you used AI, it's just because the AI solution was wrong. So anyway, technically using those tools was against the rules or whatever, but I'm not going to try to go after people and it's fine if you did that. But just, I think it's a good sort of life lessons and certainly a good academic lesson, once I grant, is that generative AI tools are useful for a lot of things, but the harder the questions are, the less reliable their answers are. And so we shouldn't sort of uncritically take their output as truth, right? So I think, if you go onto the working world and you're using these tools in your workflow, which is totally acceptable, I think lots of people do, you should just know that as the problem gets more challenging, they're going to be sort of less useful and you should be more skeptical of their output, basically. We had a question here. Yes.
Or looking up unit conversions, survey?
Yeah, looking up unit conversions and stuff. I mean, technically, I think in
Per hour to KW.
I think in lecture 2, technically,
Yes,
I put a bunch of
something
unit
about it.
things.
I was looking through it and I was like, you know what, I'm just gonna.
You can just Google
Yeah.
so the writing at the top was too strict, and I think next time we'll just say you're allowed to use kind of in the same thing as the homework. You're allowed to use whatever outside resources other than people on the exam. It's supposed to be an individual thing, but just cite your sources. And have a warning basically that AI solutions aren't necessarily reliable. So. Yeah, so Arash is a PhD student in my group, and we used ChatGPT a little bit for some of the writing on one of our academic papers, and journals basically require that you declare that in the paper itself, which is not bad practice to do in class as well.
The journals I've read through are even though I give AI credit, author credit or anything, is it interesting? It is per journal.
Don't write ChatGPT in the author list or whatever, but
Actually,
yeah.
that's true for all journals. This is just a section just before the acknowledgement, very short, that we declare that we haven't used AI.
So
they don't want any AI. If you use it for
yeah, I think some journals are more strict than others with that policy. Yeah, so if you're an academic and you're working on a paper, make sure you check with the journal that you're looking at. But anyway, so just to put a bow on the exam discussion here. So if you used a lot of AI in your solutions and you find yourself with a C or a B or something like that on the exam, it's probably not because like we're coming after you for cheating or something like that. It's just because the tool was unreliable for this exam. And that was by intention. And problem 4 in particular was constructed for that reason. So yes.
Is there any point where you will go over either in class or unrecorded or whatever, just kind of like the general solutions to each problem? Or just because I know if you may use this next year, you don't want to give out like a sheet that says the answers, but just as somebody who took it, I'd love to know, what was right and what was wrong.
Yeah, I think we will do that. So the question for folks online is, will we give out solutions basically? And yeah, I think maybe like in a video that we just put up on Brightspace or something like that, we'll do it rather than sending you guys all PDF solutions. Yeah. And then just if you're stressed out about grades, just know there will be a curve, not on the specific exam, but at the end of the class. We'll sort of curve the grades so that, it's kind of an appropriate grade distribution. So if you got slightly lower grade than you would hope for on this exam, don't freak out. If you've been keeping up with the homework and if you, put in a good effort on the project, you'll be fine.
Are the grades out already or?
The grades are not out.
Okay,
No.
Sorry, I know you
Yeah.
said you looked at it.
Yeah. No. Yeah, sorry. Just looking forward. And I know I, at some classes, stressed out a lot about grades at certain points in my career. So just trying to make you guys feel a little more comfortable. Yes.
I'm just worried because I know I'm just so.
On the midterm specifically or on homeworks? Yeah, that's a nice idea, maybe to offer you. I don't exactly know how we would do that, but to offer you an opportunity to go back, correct your own solutions, and then we split the difference. Like if you got 10 off and you submit a correction that's 100% correct, we give you back 5 points or something like that. Yeah, I mean, again, the spirit here of the exam, like I'm not trying to penalize you or whatever for not knowing something. I'm just trying to encourage you, to give you an incentive to like go back and revisit material so you hopefully retain it a little bit longer. And I think this is a nice idea for that. So yeah, we'll think about the logistics of how to do that, but we're gonna do it. Yeah. I think that's all. Any other thoughts on the exam? Yes.
I thought the spring thing was kind of random, even though I know like it's
Yeah.
creating a dynamic system, but I feel, is there a reason why you chose to do that instead of using an example that was more akin to the class?
Yeah, so why the mechanical system rather than a DER system for problem number 1? No good reason really, other than it's like a classic
I saw it.
problem
like,
for
about
illustrating this material,
10
but
seconds, I kind of panicked, and then I was like, oh wait, okay, like this is what we've done.
yeah,
But
yeah.
For a second, I looked and I'm like, wait, is this the right assignment? Did I open, like,
Did I open
something
my
else?
like dynamics homework instead? Yeah.
That is mastering are you like in dynamics?
Oh, well, I've done it in like math classes,
Okay.
but I haven't done it in like a mechanics of materials class or something, but honestly,
Yeah.
like we've learned about it in here and like applying it, although one part was a little difficult, like the E or whatever it was, but I hopefully got through it, so we'll see.
Yeah, I think the philosophy on that one was to, in part, just it's a simple problem. In part, it was to show you that like the methodology that we've been using is not like strictly for energy type systems. It's a more like if you take a controls class, you take dynamics classes, like you'll do this sort of thing over and over. That being said, we probably won't reuse that problem next year. We'll probably come up with a different example.
I like the second problem. I thought that was good. And the fourth problem, I don't know, every problem I would just kind of comb through the slides. You'd be like, okay, what do I think is gonna work here?
Right.
And I guess I found something, but
Yeah, so the fourth problem, I made some assumptions that I don't feel are correct, but I didn't know how else to do it.
yeah, that one, it was so open-ended. I was like, I feel like they're just gonna grade like your approach rather than like the exact answer.
Yeah, I don't know how we're gonna grade that one. Yeah.
Wording on there.
Yeah, I know. It was just brutal, right? And then there's like all these different unit systems and
Yes,
stuff. It was just, yeah.
It's going to getting rid of humidity. I'm like, what does that mean?
For one another thing.
We did talk about all of those ideas in lecture, right?
One lecture, so if you don't have any experience.
I don't know. I do something, I mean, we'll see. It was from the slide, but I don't know if it was from the right slides.
Yeah, see, that was pretty much, I was like, I assumed it was 0, but I also assumed it wasn't gonna be 0, because it was like, I rewanted the lecture.
You're like, it's 0, but also not 0. Yes.
But I was like, those are gonna be assuming those are gonna be the same for for all nights.
Yes.
So I just set it to 0.
Right. So yes,
Yeah, I did that.
so that is kind of the solution and the thought process that I used as well for that problem. So it sounds like you guys are on the right track.
I tried
Yes.
using like the 1 C model. Yeah, okay, and then I just set C to 0 for the steady state.
Yeah.
Okay, all right, and then, yeah, I just set QE 0.
Yeah.
Okay, maybe it worked out for me. Okay, but then, when you, did you do
Yeah,
both two
yeah.
systems?
Okay, you guys talk about this after class. We got to teach a little bit today. So I think this means that was a good problem, right? If people are like, yeah.
Yes.
It can't be the same one. That's like,
Yeah, it's like,
what delta?
The
delta T?
the QC is 0, but the delta out.
Okay, order in the court.
Oh.
All right, so again, second unit of the class, optimization. Today, we're just going to give kind of a broad overview of mathematical optimization problems, how we formulate them, how we specify them, and sketch out a little bit about how we solve them. So we'll talk about optimization problems and then just some vocabulary, basically about, what is a solution to an optimization problem? What does feasibility mean? Things like this. And then we'll talk about kind of one distinction or sort of taxonomy of optimization problems. It turns out it's really easy to write down a problem that is completely intractable to solve. Meaning you give it to a computer and you get back, either a solution with absolutely no guarantees of its quality, or it takes a super duper long time and you have no guarantees of basically about how long it will run. But there are some classes of problems for which, if we were careful about how we specify them and how we solve them, we get guarantees, both on the performance, the optimality, and also on the runtime. So we will talk about those things today. So just our goal here isn't really to make you guys experts in optimization, right? You should take an optimization class or maybe multiple if you want to get to the level of true expertise. But we want you to basically become good users of software that, again, allows you to solve interesting problems for DER applications. So yeah, optimization is an enormously broad and incredibly deep field. It encompasses a wide range of problems. So most physics problems, for example, you can frame as optimization problems. Light, when it's traveling through different media, follows what's called the principle of least time. So you can solve for the path that a light would take through a prism underwater by basically specifying an optimization problem and saying what would be the fastest route for the light to travel. In mechanics, you can, so there's Newtonian formulation of the laws of mechanics. You can also use what's called the Hamiltonian or the Lagrangian formulation, which basically use a principle of least action or a principle of least energy to kind of come up with the governing equations for a dynamical system rather than doing F equals ma and stuff like that. So anyway, there are hard problems in all of those fields, and the fact that they can always be framed, or many of them can be framed as optimization problems, should tell you that optimization is in some sense super hard, right? It's as hard or harder than all those fields in terms of solving it numerically, basically on a computer. Right, so most problems that we can write down on paper, it turns out are very hard to solve, either with pencil and paper techniques or with a computer. But there is a class. In fact, there are multiple classes of problems that are usually solvable. And one is called convex optimization problems. And convexity is sort of a curvature property. So a convex function you might call concave up or bowl-shaped. So if you have a function like that and the set of solutions, possible solutions you're optimizing over is also convex, and we'll talk about what convexity means for sets, then you get these guarantees that there are algorithms that can solve fairly quickly. You have guarantees on the optimality of the solution that they return, and so on. And so there are many applications for convex optimization. DERs happens to be one really nice one because it turns out that many of the problems that are interesting, not all of them, but many of them that are interesting in this class can be formulated in this convex setting. Yes?
Ask just what rich theory is. It seems interesting.
Yeah, what does rich theory mean? So basically, okay, so there's a field of math called analysis, and that's basically the sort of graduate level version of calculus. So if you take a class in real analysis, it's basically the calculus of real numbers, but done at a more kind of theoretical level than what you would take in an undergraduate calculus type class. And there is a subset of analysis called convex analysis, the specific properties of convex sets and convex functions and things like that. And so there are many mathematical theorems that come out that talk about sort of the geometry of these problems, convergence of algorithms and things like that. So there are many like kind of interesting theoretical guarantees that you can get out of. And that's some theory from convex analysis, basically. Yes. Yep. Right. So here we're basically just going to scratch the surface of this stuff. You can take a whole class, in fact, multiple classes just on convex optimization. And of course, if you want to learn about non-convex optimization, you can take classes on that as well. Okay, so here is a basic form, not the only way you can specify an optimization problem, but a pretty generic form. So the idea is to choose what's called the decision variable here, x, which is a vector, in general, an n-dimensional vector. So it's just a long list of numbers. N here could be 2 or 3 in a low-dimensional kind of geometric type problem, or it could be a billion in a big, someone was talking about a deep machine learning class, Grace, that you're taking, and there you might be optimizing millions or billions of variables, potentially. And then we want to minimize what's called the objective function, so f with a subscript 0 of x. So it's some scalar valued function. Here, f maps a vector, an n-dimensional vector, into one number, a real number. And then we have a number of constraints. And these are all formulated as some function of x being non-positive, being less than or equal to 0. And of course, you can formulate this in other ways, but this is actually, although it looks kind of simple, this is actually a very general formulation. And so to solve this problem, basically, you would need both a good algorithm, but you would also need basically to specify these functions, the objective function and then all of the constraint functions. So yeah, how do we interpret this sort of verbally? Our goal is to choose the best feasible n vector. Feasible means it satisfies all of the constraints. And best means with respect to the objective function, it has the lowest kind of possible value. So right, x here is the variable, and it's just a long list of numbers. The objective here in a minimization problem would basically quantify how bad a solution is. And so we're looking for basically the least bad solution. You can also formulate maximization problems, which there the objective would be how good something is, and so on. And then x is feasible basically if all of the constraint functions are satisfied here. So f1 through fm of x are all non-positive. But also there's kind of a more technical condition that basically says that all of the functions have to be sort of well-defined at the value x. So just as an example, there are some functions that are only defined for certain values. So log is only really well-defined for real numbers at least that are positive, strictly positive. And so, what would it mean for an x to be that was -12? How do we detect if it's feasible or not when we want the log of it to be non-negative? Well, that's not really well posed because we can't really evaluate the value of log of -12. Okay, so just a couple of quick DER examples here. You can think of, for example, sizing or designing a solar photovoltaic array. So here, our decision variable might be something about the size, maybe the number of panels that we put up on a rooftop or out in a field. And it might also be the orientation angles. So how do we tilt it and orient it kind of laterally as well? We might have a range of objectives. So it might be the initial cost of all the hardware and the electrical work and so on. We obviously want to save some money on our electricity bills, so that would factor into it. We might care about greenhouse gas emissions, so how much can we eliminate? And there might be a bunch of constraints related to how much money we have to spend. Basically, we might have only a certain amount of land available or a certain amount of rooftop area. And then we would also have some equations that basically come from the solar photovoltaic lecture that we talked about that would describe, as a function of how big the size is or how it's oriented, how much power we get out over time under different weather conditions. Another example would be electric vehicle charging. So here, the decision variable we want to choose might be the charging power, or if it's a bidirectional vehicle that can discharge into the home or building as well as charge, then we might also look at discharging powers. And we have some planning horizon. This could be looking ahead a day or a week, something like that. And again, we have a range of possible objectives. And so this might include, charging at least cost. If you're out on the road, you might want to choose charging stations that get you to your destination quickly. So you might want to minimize the time spent driving and charging. Again, there might be emissions considerations. So charging at home, maybe you could do cleanly off of solar, off of your roof. Charging at work might be less clean, something like this. And then, yeah, we have constraints, again, that come from basically how much energy we can store in the battery, whether we can discharge into the home or not, how quickly we can charge, and so on. And so the battery dynamics as well, the equations that we've sort of seen come up time and time again with different DERs, those would enter in basically as constraints in the optimization problem. All right, so now I'm just going to go through a bunch of sort of gymnastics that show that this problem, which looks kind of deceptively simple, is actually pretty general and can model a bunch of different types of problems. So to do that, we'll basically show ways you can get equivalent optimization problems that basically have the same solution. So two problems we say are equivalent if a solution to the first problem sort of easily gives you a solution to the second problem. So you can transform it in some way and say, okay, this is the solution without having to solve the second problem independently. And then vice versa. So basically you can solve either one and they're interchangeable in terms of giving you the result, the solution that comes out of it. And by the way, the solution means just the value of the decision variable of x that you get out of the problem. So one way to kind of convert between equivalent problems, you may say, well, look, you wrote down a minimization problem, but what I want to do is maximize the amount of money that I can make from operating my DER or something. So suppose that we have a maximization problem and some other function g, rather than our objective in the minimization problem f0 or f0. And so g measures basically how good x is rather than how bad it is. And we want to now choose x to basically maximize this function g, to find the most good thing. And again, we have some constraints. So this problem is mathematically equivalent to just the problem of minimizing negative g. So if g quantifies how good something is, negative g you can think of as quantifying how bad something is. And so we could solve this minimization problem, but get a solution to the maximum. Yes.
I guess try to minimize to like the absolute value. Does that help with convergence more if it's a 1 over g versus negative g?
Oh, I see. So the question is basically to flip the max to min, could we minimize 1 over g rather than minimizing negative g? And the answer is probably yes, although it might change kind of the structure of the optimization problem in a challenging way. But there may be situations where 1 over x is better than negative x. Yeah.
That's just what they had us do for a different class, somewhere where they set up the code is always 1 over x.
Interesting. Yeah. Well, I think we'll talk a little bit about that transformation and why it works in just a sec here. Another very simple thing is, okay, well, what if I have some constant? So I know that it's going to take a certain amount of labor and therefore a certain amount of money in order to install my PV array. And that's just related to rolling trucks to the sites and having people on staff and so on. So that's going to be a constant independent of how big, for example, my solar array is. Well, this problem, it's straightforward to show that you can basically just drop that term because we can't influence it via the choice of x. So here, this is an equivalent problem. We could solve this, get the solution x, plug it back into the objective here, and then just add in the constant a, which could be 1,000,000 or negative 12 or whatever. And that would give us basically the value of this problem. Transformation of the objective and the constraint functions are another way to get sort of one equivalent problem from an original problem. And the sort of 1 over x transformation, I guess, satisfies this. So suppose we have some function h, which is an increasing function, which just means that if you have a larger value of the input variable, then you get a larger value of the output from the function. And then we have some list of functions which basically satisfy this property here, so that if the argument of the function is negative, then the function value at that y will also be negative. So suppose that we have functions that satisfy these properties, then the initial problem here, kind of in the original form, is equivalent to this transform problem, where we take h, this increasing function of our objective, and wrap it around the objective function. And then for the constraints, we take each of the g's and kind of wrap them around a corresponding value of the f's. So something that often people do would be taking either an exponential or a log in order to basically simplify the structure of the optimization problem, make it easier to solve. Okay, the constraints that I wrote down all had the form sort of fi of x not bigger than 0. But what if you have a right-hand side function here? Well, you can write that as fi of x no larger than 0 by just defining this new thing. So subtract off the h, and then we get a 0 on the right-hand side here. And you might have a greater than or equal to constraint rather than a less than or equal to. Well, in that case, you just subtract off the g. And again, we can define this function kind of in the given form so that what we want to do is to make it less than or equal to 0. Equality constraints. So the dynamics that show up in most of our DER problems, for example, we have a battery evolution of the energy stored in a battery, the evolution of the temperature in a building, things like that. That have basically, we went through all this modeling gymnastics to come up with algebraic equations that they're equations. They have an equal sign in them, not a less than or equal to, an inequality. And they describe how the battery or the temperature or whatever evolves over time. And so what if we have some of those in our optimization problem? Well, you can always convert an equality constraint like this into a pair of inequality constraints. So this thing here holds if and only if both of these things hold. So if g is less than or equal to h and greater than or equal to h, then the only possibility is that g is equal to h. And then we can kind of do our gymnastics again from these inequality constraints with non-zero right-hand sides, and then we write down basically functions in the original form that I described. By the way, eventually, we're over the next 3 lectures, we'll build up to introducing a tool, an optimization tool called CVX in MATLAB or CVXPy in Python. And those tools will do basically these optimization modeling gymnastics for you. So you won't need to implement these things in your own code. I just want you to sort of build an understanding for the fact that these optimization problems are actually quite general, and there's a lot that you can do on the front end, the modeling end, to basically put things into a solvable, clean form. Okay, a feasibility problem is basically an optimization problem with no objective. Yes?
For the last one, why can't we not just say g minus h equals 0?
Yeah, why can't we say g minus h equals 0? So then we would still have an equality constraint. And if we look at the original problem that I formulated back here, sort of this standard form problem, at least the way that I have written it down here. There are other ways to write this down where in addition to having these inequality constraints, you would have equality constraints. And actually sometimes for designing algorithms, that's better. Sometimes it's easier to handle equality constraints than inequality constraints. So you might want to leave them in as equality. But I'm just trying to show that this form is sort of pretty general. Yes?
Sort of on the same note, I think I'm missing something. If we're looking, we're trying to optimize something and we're looking for the best solution, why then wouldn't we want inequality, which has kind of more of a rigid answer, and we instead look for an inequality, which in my thinking would have more answers,
Yeah, so
through the model or
It converges on a single value. The constraints are their inequality, so it will accept all values less than x.
I see. Okay.
But then they find that the best value is y.
Okay.
Yeah.
So it just helps you lower down what you're searching.
Yeah, in terms of rigidity is
Okay.
force it to
Can't move or
you
anything.
can't go anywhere besides this. Then you can't look
For better solutions.
I mean,
I mean,
I guess
fall on.
my answer to your original question of why wouldn't you want equality constraints is they're fine. And in fact, we can include equality constraints in this formulation. It just, for whatever reason, I chose this as the sort of standard form to write down. And so you would basically have 2 inequality constraints rather than 1 equality constraint. But mathematically, it's equivalent, and the solution that you get would be the same either way, usually. Okay. So yeah, feasibility problems are basically optimization problems where we don't have an objective. So you don't say necessarily, oh, I have some way of judging, which is worse between two values of X. You just say, all I want is some value of X that satisfies all of my constraints. So just give me any solar photovoltaic array such that I don't pay any more than $1,000 a year for energy, and it doesn't take any longer than 1 year to install or something like that. And then you say beyond that, I'm sort of neutral to the solution. So this is equivalent to an optimization problem where you just put a constant, call it 0 for simplicity, into the objective function, and then everything else is basically the same. So as an example, solving a system of simultaneous nonlinear equations can be framed as a feasibility problem. So suppose that we have a bunch of nonlinear equations. These are all scalar valued, but you could have a system that are coupled through the choice of the variable x here. And we might want to solve 1 million of them and come up with one value that satisfies all of these equations. So this thing we can write as a feasibility problem that basically says find any x such that all of these things, which are just transformations of the equality constraints, right, into inequality constraints, such that all of these. So here we have 2 times m constraints, where m is the inequality constraints, where m is the number of equations that we're trying to solve. Okay. So solving a system, a high-dimensional system of nonlinear algebraic equations is not a trivial problem. There are ways to do it that are pretty reliable and so on, but they don't always work, and they can take a long time to do. So the fact that that problem, which is already pretty hard, can be cast as kind of a simple version of an optimization problem, again, should tell you that optimization includes a lot of hard problems. All right, so I just want to go through some vocabulary here. There's a lot of this, and you can always reference these slides kind of as needed. So a problem is infeasible if there is no x, no n-dimensional vector x, such that all of those inequality constraints f1 through fm less than or equal to 0, so that all of those constraints are satisfied. So just as one kind of simple example, a ginned up example, but this actually occurs in practice more often than you might think. Suppose we're trying to find a scalar number, just x, subject to a constraint that we want it to be bigger than 2, but we also want the square of x to be no bigger than 1. So the things that are feasible for this constraint here are the things that are between -1 and 1. But here we want something that's bigger than 2. And so there's a clash, right? There's no x that satisfies both of those. So you can think of this roughly as a badly specified problem. But sometimes just learning that your problem is infeasible is actually valuable information. It can tell you about whether your goals are realistic, for example. An optimization problem can also be what's called unbounded. And so here, like kind of in just words, this basically means that there is no limit to how good your solution can be. So you can find some sequence of variables, x, call them x1, x2, x3, and so on, such that if you evaluate the objective at each value of these x, it just keeps getting better and better, smaller and smaller, as k increases. And so an example there, again, is kind of simple ginned up example, but this does happen in real interesting problems, is suppose that we just want to minimize the log of x. And here, so our feasible region would be the set of x for which log is well-defined, if x is a real number, which is just not strictly positive x. So negative numbers are infeasible here. And then to come up with this sequence of x that it just gets better and better, well, let's start at x equal 1, and then let's just divide x by 2 at each iteration. So we have half, a quarter, an eighth, and so on. And so as you go, you just keep getting better and better and better objective values. So there is no limit to how far down the y-axis you can go here, and that tells you that this problem is unbound. Okay. So let's talk about optimality. So a variable x, we typically put a star on it if we call it optimal. It's optimal, or you could call it an optimizer for your problem, if it is feasible, which means all the functions f0 through fm are all well-defined at x star, and it satisfies all of the constraints. And then so that's feasible, basically. And then in addition to that, it is optimal, which means that the objective value is no larger, or sorry, for any x that is not equal to, or sorry, for any x could be equal to x star, but any option you can come up with, the objective value will be at least as big as the objective value of x. So in some sense, this tells you this is as good as you can do. So in feasible problems, we say that there is no optimizer. So an algorithm would basically not give you back a response. It would just say infeasible. And unbounded problems as well, we typically say there is no optimizer because you can just move in some direction and get better and better forever. And a feasible problem that is also bounded, so it's not infeasible and it's not unbounded, it can still have multiple optimizers. Just as one example here, again, a silly ginned up problem, but these effects can happen in big and interesting problems. Suppose we're in the plane, so we're looking for a two-dimensional variable x. Call it x1 and x2, or you can think of them as x and y. And we want to minimize the second component, so the vertical guy here, subject to the constraint that we're on the line, x2 is equal to 1. It's a very dumb problem, right? It's very easy to solve, but actually this whole line contains an infinite number of solutions that all have the second component of x equal to 1. So this entire line is optimal. It tells you that in general, an optimizer is not necessarily unique. And so if your algorithm that you run to produce an optimal solution, it might, you run it 2 times, it might give you back two different solutions that might be quite different. But the idea is that they would have the same value of the objective function, f naught. So this thing costs $12 and this thing over here costs $12. They look very different, but they give you the same sort of objective. Okay, so there's what's called local optimality and what's called global optimality. The previous slide was really about global optimality. So this says, look at any feasible x, right? So any x that satisfies all of your constraints. It's optimal, basically, x star is optimal if you beat or tie any other possible feasible solution. Local optimality, again, means, so we call it x tilde here. So this locally optimal solution or a local optimizer is, it must be feasible. And then there must be some neighborhood of x tilde. So you can draw a little ball or a little region around x tilde such that within that little neighborhood, there is no strictly better solution. So x tilde, again, either ties or beats everything else in the neighborhood. So here is kind of a sketch of that. So here, our blue function here would be the objective function. We're just, I guess, dealing with a scalar variable here, so one-dimensional optimization problem. So here, the globally optimal x star would be at the true sort of bottom of this function. But x tilde is at least as good as everything kind of in this neighborhood here. So you actually have to get pretty far away from x tilde over to here before you get a solution that is better, strictly better, meaning a lower value of the blue function. And so it's actually pretty easy to come up with algorithms, not necessarily easy. There's certainly an art to it, but not too hard to come up with an algorithm that would give you a local optimizer, a local minimum. But if you are unlucky, and typically we have no guarantees on how good or bad the solution is, this guy here might be far worse than the value of this guy over here. Yes?
Is local optimal basically useful for us at all? Or we're always looking for these basically the non-local ones. The one the name I just forgot.
So local versus global. So the question is a local solution, a local optimum, or a local optimizer useful for us at all? The answer is yes, absolutely. So all of the technology that underlies the explosion of machine learning and artificial intelligence, a huge amount of it is powered by neural networks. And the way that we train a neural network, which means optimize the parameters that are in that model. So those algorithms, those optimization algorithms, in general, you have no guarantees that you get to the true global minimum of the function or a global minimum. Very often they get to local minima, but they end up being extremely useful. You can do very powerful things with them. So yeah, local optimization is a science in itself and also a useful thing, for sure. Yeah. Question, yes.
Is there, given what you just said, this is kind of, but could you just change your parameters in a way that you would be guaranteed to find a global minimum or a global optimal solution?
So you're saying you're supposed to, suppose you're trying to write some code to solve this problem. Is there something you could do, changes you could make to your code to sort of knock you out of this like valley and into the deeper valley
Yeah,
over
or
here?
could you just keep saying, okay, I found the local optimizer in that, neighborhood. Now let me just cut off after, say, okay, now we need to be after that neighborhood. And then let's look for the next one, and you just keep searching through.
Yeah, I could. So can you dream up algorithms where, say you get sort of stuck over here, maybe you start over and you start searching over here,
Yeah.
and then maybe that gets you down here. Yes, absolutely. And again, this is like a whole science, and people definitely have come up with methods that tend to do that.
Okay.
Yeah, for sure. But those methods often either take a long time to run or have no like guarantee to their performance. Yeah, it's at least decent. And pragmatically, often you start with like a solution or a tentative solution that you come up with. You're like, well, I think this design would be pretty good. And you would feed that to an algorithm as a starting point. And then a local minimization algorithm would say, well, I'm going to give you back something that's at least as good or maybe better than that. So it's going to improve, right?
Yeah.
So which is valuable and useful. It's just won't necessarily tell you, and by the way, this is the best you can do. You can stop looking for improvements, right? Usually. Okay. So that's some vocabulary. And then we'll talk about tractability of optimization problems. And this feeds into the notion of convexity and why we're interested in convex optimization problems. Not exclusively, but significantly. Okay. So the idea here is, again, that it's very easy to write down an optimization problem on paper that, that is just totally intractable to solve, which means, at least in the way that I'm interpreting it today, that either your algorithm for solving it on a computer would take a super duper long time, or at least there'd be no guarantee that it won't take a super duper long time, or it'll be fast, but it gives you back some solution that you have no guarantee on how good or bad it might be. But there are some problems that can truly be solved to global optimality in guaranteed sort of fast times. So the way that we typically differentiate between kind of a fast and a not fast algorithm is using by describing how long the runtime is in terms of the dimensions of the problem. And so typically the dichotomy between sort of tractable and not tractable is basically, can you come up with an algorithm that will be guaranteed to solve your problem in a polynomial time. So you can upper bound the runtime with a polynomial function of basically the size of your input data. So if, yes, there is some polynomial, and it could be a 2 millionth degree polynomial, but some polynomial, then you call your algorithm good or polynomial time. And if not, then it typically has exponential or worse time. And that typically is a slow algorithm. So why do we care about polynomials versus exponentials and so on? Here is a graph. So here n you can think of as like the dimension of the vector that you're trying to solve for, something about the size of your optimization problem. And this is pretty mild values of n. We're just going from dimension 0 up to dimension 100. The y-axis here is logarithmically scaled. So 10 to the 20, 10 to the 40. So these numbers are like kind of about getting to the scale of sort of the number of particles in the universe and stuff like that, enormous numbers. So all of the polynomials here, the lower three lines, the green, purple, and orange or yellow, I guess, these are all polynomials of degree 1, 3, and 5. And they all look basically flat on this logarithmic scale. And then the exponential thing here grows what looks like linearly on this log plot. And then the function n to the n, just for comparison, looks kind of quadratic or something like that, even on this log scale. So the idea is that whatever your polynomial is, there's going to be an enormous gap between the polynomial time and the sort of exponential time for an algorithm, even if you're degree 11 or 27 or something. Does this make sense? Okay. So again, it's very easy to write down a problem that in fact, there are no guarantees that it can be solved in polynomial time. Here is one. It's a famous problem called the knapsack problem. And I guess before getting into the math, just verbally, what this problem more or less represents is, imagine you're like a cat burglar, and you just did some second story work. You broke into somebody's house or apartment, and you're in the bedroom where all the jewelry is kept in a box, and you have only like a little satchel, and you can only fit so many things in there. And so your goal is basically to maximize the value that you can abscond with. And so you have to decide, here's a diamond and here's a ruby, and but this is big, but this is small, and so on. And so the objects have different sizes and different values. And you're trying to cram as many of them as you can into your knapsack, I guess. The word knapsack is a little antiquated, and that's because this problem goes back at least to like the 1940s. Okay, so mathematically, we're trying to choose an n vector, which basically we require to have either a 0 value or a 1 value for every entry in that vector. So this basically means yes or no, should you stuff it in your backpack, your knapsack. And then we want to maximize this inner product, C transpose times X, which is just C1 times X1 plus Cn times Xn, where C's here are basically the values of the different objects. And then we have a constraint, and this basically, B you can think of as sort of the carrying capacity of your bag, and A something about the volumes or the sizes of the objects that you want to run away with. Okay, so fairly simple problem, linear objective function, one linear scalar constraint, and then just this sort of benign looking thing that either you can be 0 or 1, which seems like it should make your problem easier, right? You have a limited number of choices rather than kind of any real number you can think of. But it turns out that this problem is what's called NP hard. NP stands for non-deterministic polynomial. So an NP hard problem, actually this problem is what's called NP complete. So an NP problem, first of all, by the way, why am I talking about P and NP here? Basically, this is what's called solving, not the knapsack problem specifically, but I'm showing that the set of things that have guaranteed polynomial runtime, and the set of things that are NP, not deterministic polynomial, which means if I give you a solution, you can verify whether it is good or not in polynomial time. But there's no known way to solve it, to generate a new solution in polynomial time. So if those two sets are equal, then P is NP, and you earn $1 million. And it turns out that if you can prove a polynomial time algorithm for the knapsack problem, it's what's called NP complete. So it's as hard as any other problem in that set NP. So you have proven that P equals NP, and you get $1 million. This is sort of one of the big mathematical problems. Whose bounty is that? So I think it's called, actually don't know who offered up, but there are 7 Millennium Challenge prizes, and they were framed, I mean, many of them long time ago, but they were sort of codified in the year 2000. And they put this $1 million bounty on each of those. It's a foundation that basically is about mathematical education and stuff like that. And one of the 7 has been solved. So after 25 years, we've got one. I don't know the name of it. What's that?
Will Hunting.
Oh, Good Will Hunting. Yeah. Yeah.
There's something interesting, and I guess these are the unsolved mathematical equations.
Yeah,
right now.
yeah.
And one of the things that these people in AI industry want to do is basically solve these questions. So this complicated AI algorithm.
Yeah, why not, right?
One of those actually is non-Aristotle's equation.
Yeah, right. So one of the problems, there are 7. One of is the Poincaré conjecture, but one of them is basically showing that there's guaranteed existence of a continuous solution to the Navier-Stokes equations, which are some of the big governing equations in fluid mechanics, right? So yeah, so your point was that one thing people are trying to do in the world of AI is to come up with models that can solve this.
But
Good luck.
so I'm a little bit confused because you're saying that, like, if you could prove this, you would say that you're proving that P equals NP. Which
Yeah.
in theory isn't right, but like, so is it impossible for it to be true, or has just been
It's possible for it to be true.
Okay.
Yes, I think the strong intuition among computer scientists is that it is not true, but it sort of hasn't been determined either if it's true or not.
I see.
Yeah,
So
yeah. Right. And so loosely speaking, there's like this set of problems that we know we can solve efficiently, and then there's this set of problems that like maybe we can solve efficiently. Like you can verify a solution efficiently, but can you produce a solution efficiently? And if you can solve a knapsack problem, it turns out that you can solve kind of any problem of that difficulty. And so then we kind of expand the set of problems that we can solve efficiently. And that would be cool. It'd be powerful.
Solve. And just from your explanation, It
Yeah.
seems simple, but obviously I'm missing something, clearly.
Well, so they're what are called heuristics, which are things that are probably ways to generate probably good solutions, but not necessarily like the best possible solution, right? And so there are good heuristics for the knapsack problem. It's not hard to come up with one. Like start with the highest value item, put it in your bag, and then proceed down the list.
Yeah.
The problem is, what if you have like a really big, really high value item, and then what if there are some small, not that high value but close items? So anyway, there's subtlety to the problem, but getting a little bit off track here. Sorry. Okay, so what are we talking about here? We're talking about tractable optimization problems. Roughly, that means polynomial time algorithms exist for the problems. That's a notion of tractability. It's very easy to write down an intractable problem, or at least we think an intractable problem. And so there's this distinction then between local and global optimization, finding a good solution or one that's better than your kind of starter solution versus finding a guaranteed sort of best solution. So a local optimizer, typically we can compute them efficiently. Again, polynomial time algorithms, but there's usually no guarantee on how good or bad that solution might be. And in the worst case, you might be much, much worse than a global solution. And then conversely, a global optimizer, it gives you a guarantee. You found it. Okay, you did as good as it is possible to do within your feasible region. But it might take a super duper long time to compute. In fact, you might have just explosions in the runtime. And then there is a class of problems called convex problems for which all local solutions are provably global solutions. So loosely, this means that you can use the kind of algorithmic approaches that we use for local optimization. And then for free, you get this certificate that when you're done, you have found the best thing that is possible. So that's cool, and it basically is useful. So again, for convex problems, there are good algorithms. There's a lot of theory that kind of provides these nice guarantees and so on. And DER problems very often fit into a convex framework. The sort of cost of moving into that framework is that it requires a little bit of math and kind of coming up with roughly a calculus of curvature and monotonicity so that we can understand what functions are convex and what compositions of different functions are convex and things like this. And then once you have that knowledge, you can use tools in an effective manner to solve interesting and challenging problems. So we'll talk about that over the next couple of lectures. For now, I will just go through a couple of examples. One, a very famous problem, an optimization problem, is called least squares. And this comes up in various forms, kind of in many, many different fields of science and engineering. The mathematical problem statement looks sort of bland and generic, but it turns out that it can model an enormous amount of phenomena. So here we want to choose an n-dimensional vector, and we want to minimize this weird looking thing. So here A is a matrix, an m by n matrix. So A times x would be an m-dimensional vector, and then B is another m vector. So this difference here is a vector-wise subtraction. And then this whole thing is an m vector, and it's a transpose, so it would be a row vector. So we have a row here and a column here. So the overall value of this thing would be a scalar. And it basically, each element would have kind of the square of the difference between an AX component and a B component. So roughly, this is a way of saying I want AX to be close to B. And technically, the condition here is that the number of rows here should be at least as large as the number of columns. So we have more equations than we have unknowns, basically. So the idea here is that we're trying to find some x that roughly satisfies the equation AX equal B. But again, this is an overdetermined system of linear equations. So there may not be any x that solves all of these equations exactly. And so we want to find something that approximately solves these equations. And the notion of approximation here basically is framed in terms of the squared deviation of the left-hand side from the right-hand side. So there is theory we'll go through in just a sec that basically says you can write down, without using a numerical algorithm, you can just write down the global solution to this problem. There are no constraints, so you don't have to worry about feasibility. And it turns out that the solution has this form. So you take A transpose multiplied by A, invert that matrix, and multiply by the transpose of A times B. And actually forming all these matrices, doing all the multiplications, the inversions is usually a pretty slow way to solve this numerically. And there are much faster ways to solve these equations. And in MATLAB, the backslash operator, which is very overloaded, does a whole lot of really powerful stuff. But when you give it sort of a problem like this, it gives you back the global solution, the least square solution. And here the runtime, the solve time for this algorithm is proportional to n, the number of columns squared, times m, the number of rows. So this is a polynomial in m and n, and so we get a polynomial time solution for least squares. Do you have a question? Okay. Okay, so where does that solution come from? Real quick, so if we have a quadratic function of an n-dimensional vector, so this is a generic quadratic function, we can write that as x transpose times px. So you can then think of this in the scalar world as a number p times x squared plus qx. So this is the linear component. This is the quadratic component. And then there can be a constant component as well. And then actually, without loss of generality, you can assume that this P is a symmetric matrix, meaning P is equal to its own transpose. And it's square. So the gradient of this function, and you can prove this by writing out the components and taking derivatives and stuff like that, but the gradient is basically what you would expect by generalizing the scalar notion. So suppose we had a scalar function, px squared plus qx plus r. Well, the derivative of that would just be 2px plus q. And that, it turns out, generalizes to the gradient here as well. And so in least squares, we are trying to minimize this thing here. This is our objective function. And it turns out that that is a quadratic function, and you can come up with what the p, the q, and the r are for least squares. So I guess I'm just going to rip through this, and you guys can look at it on your own time if you like. But basically, here we find that p is equal to a transpose a, q is equal to negative 2b transpose a, I guess that would be q transpose rather, and then r is equal to b transpose b. So if we take that, this is a quadratic function, and we have an expression for the gradient of a quadratic function. So take the gradient and then set it equal to 0, and we get this system of linear equations here. So if we move the negative term here to the right-hand side, the 2's cancel, and we get the expression that showed up on the previous slide. And then for this inverse to exist, we need A to be full rank, meaning the number of linearly independent, or sorry, the n columns of A are linearly independent.
I think that in the MATLAB, what will we do for the first term there?
Yeah, so the question is what to do in MATLAB. So if you have a least squares problem and you want to solve it in MATLAB, you just type x equal a backslash b. Yeah. You can type all this other stuff if you want to. You could put in an inverse INV of a parenthesis, or sorry, not parenthesis, apostrophe. That's how you do transpose in MATLAB. So a apostrophe a and so on. So you could type all this out and you would get the same thing. It would just take a lot longer. Okay, so one interpretation of least squares, and again, there are many, but is what's called model fitting. And so we've mentioned, machine learning, data science, AI type applications a couple of times. So model fitting is a classic problem in that field. And so the least squares interpretation in the kind of way that we've written it here would be that each element of B is some target that we want to predict. So this could be, for example, the price of some stock on the stock market, or it could be the output of a solar panel at some time. Or it could be the demand of electricity from a whole community, for example. And then each of the elements A, I, J are observations of features, which are basically things, information, data that have some predictive power in your model that we're using to try to make predictions of this target BI. And we would love to come up with a model that exactly hit, so AX exactly hit B for every example that we are given. But typically we can't exactly, but we want to come up with a model that basically is close. And so X here would be the parameters of the model, the things that we're optimizing for. So this is not exactly like a neural network type thing, but the weights in a neural network have a similar interpretation. So this would be called training the model, is coming up with the values for these weights or parameters. And so the problem here is to look for some X such that for each value, each example that we are given, each I that we're given, AX roughly equals P. So we can write down the least squares objective, and this thing basically penalizes errors between the thing that we're using as our prediction and the target that we're trying to. And it penalizes them in a square sense. So this thing is equal to 0. You get no penalty if you're exactly right. And then the further you get away, the higher penalty you incur, basically. So that is one classic convex optimization problem. There are many more. Another is called linear programming. And the idea here is that you have a linear objective function and you have a bunch of linear constraints. So this isn't written exactly in the standard form that I showed you guys, but it's very close. So here the notation, this like weird inequality thing here, just indicates element-wise inequality. So that means that for every element here, yi, it's less than or equal to zi. And unlike least squares, there is no known analytical solution for linear programming problems in general. But there are good algorithms that can compute them, and it can do them in a solve time that's basically the same as least squares. So it's basically the same as solving a bunch of linear equations. And there are many tricks you can go through to transform problems that are not kind of natively, as you write them down, linear, in that you might have a nonlinear objective, you might have different constraints that aren't linear either, but you can often use tricks to kind of put a problem into a linear programming form, which can be very useful, again, because it's easy, not easy, but there are good algorithms for solving linear programs. So one example here is another model fitting approach, but rather than minimizing sort of the average deviation of our predictions from our targets, we want to minimize the worst case deviation. So you say, I don't care if I miss sometimes, but I want to guarantee that, or what I want to do is minimize the worst possible miss, something like that. And then, so instead of having this objective, we just have a maximum absolute value objective. So again, the thing on the right-hand side here is 0 if our prediction, this sum over here, exactly equals our target, the b term here. But then as we deviate, we do it in a kind of absolute value sense rather than a quadratic function sense. And then rather than looking at the sum of all of the errors, the misses, we look at the worst case value of that. So I want to wrap up, and we only have 4 more minutes. So there are a couple of slides here that basically show that this thing, which is not linear, right? The absolute value function is not a linear function. It's a piecewise linear function. But it turns out that you can actually reframe this problem, which is called Chebyshev approximation. You can reframe the problem as a linear program, and then again, generate solutions quickly with good computer algorithms. But I'm not going to go through this. I encourage you to look at it. I just don't really have time. But these are some transformations that you can do on the different things. So here I'm showing an example of a fitting problem. So basically we have some data here. These are the black points. And we want to come up with a function or a curve that roughly matches the black points kind of in the best way that we can. And we have 2 different solutions to this where we basically specify 2 different problems, 2 different versions of what best means. And so in the least squares thing, we say, well, we want the best basically average, the least average squared deviation. So look at all the errors, take the squares, add them all up. We want that thing to be as small as possible. And the Chebyshev, again, takes the sort of worst case approach. And so here we're looking at histograms of the error, basically the miss between the blue function and the dots, or the red function and the dots. And so the least squares thing is often 0. And the sort of distribution here is centered around 0. And we underpredict roughly as much as we overpredict. But in the worst case, we miss by -2.5, something like that. In the Chebyshev approximation, actually now the distribution is kind of tilted, but we have kind of crammed what's called the support of the distribution, basically how far it goes left or right. Rather than going to -2.5 here, it only goes to maybe -1.8, something like that. So this is the worst case miss over here. And it's actually, even though the average miss is kind of large, the red line is often quite far from the kind of bulk of the black data. There are these outliers up here, and the red curve actually gets closer to those outliers. So we don't miss by as much as the blue curve misses. So if you're taking kind of a conservative worst case approach, you might prefer the Chebyshev solution to the least squares solution. That being said, least squares is like used all the time across many, many fields of science and engineering. Chebyshev approximation is a nerdy niche thing that is not used very much. And just staring at the data, like which one qualitatively to you looks like it's like roughly fits the data better.
Squared.
Yeah, the blue one for sure.
Would
Yeah.
you ever do like a reverse Chebyshev if you want to be concerning the best value would be a high value, like where it would go down below to meet the, I guess, meet the down to -2s and.
Um, so the question is, would you ever try to do like a reverse Chebyshev thing where, well, I'll interpret this as that there is a field called basically robust statistics, which tries to come up with models like this that fit kind of the core, the bulk of the data, and that are not very sensitive to weird outliers like this. And by the way, I ginned up this data and I specifically put a bunch of outliers up here to show the difference between these approaches. But so there's something, yeah, in robust statistics, you want to do kind of an opposite Chebyshev thing. You want to allow your model to say, yeah, like sometimes you can miss by a lot. If there's like a weird point that's like obviously an erroneous data point, then don't worry about fitting that. Like, don't bother with it. Just try to fit the core of the data.
I think more so like, we do this, we sell this car, and 9 times out of 10, we sell for $800, but one time we sell for $1 million.
Oh.
So I'm gonna bias towards the outlier and say we're gonna sell it on average for $500,000.
Right.
Like, we would never do that.
Right. Yeah.
Teaching machine design for undergrads. Typically, a lot of the plots they use are for like failures for bolts and whatnot.
Yes.
You want to be below what often fails, so that way you're catching pretty much almost all of the, except for maybe the sporadic bolt that just broke at 1 pound. You want to, like at 95, 99%, they're not going to fail if you stay below this curve. Stuff like that.
Yeah, so you guys are bringing up very, I think, subtle and interesting questions and distinctions here. And I think in my mind, a lot of this goes to sort of showing the value of learning about optimization modeling and these distinctions and themes. Do you care about, missing only a little bit? Do you care a lot? And how does that go into specifying sort of the problems that you want to solve? So that's kind of one side of knowing about optimization, is knowing kind of how to formulate problems in a clear, consistent way that really expresses what you actually want to happen from the system. That's kind of one half. And then the other half is, okay, given a problem, how do you solve it? And there's a kind of interplay between those two. But mainly, I think we want to focus on the first one in this class. All right, so yeah, so we talked about least squares, we talked about linear programming, and then general convex optimization is basically the problem that I started with. But all of these functions, rather than being kind of generic functions, are convex functions. And so next time we will talk about what it means for a function to be convex. But the basic takeaway here is that just like with linear programming, there's no known analytical solution in general for a convex optimization problem. But we have lots of good algorithms to solve them quickly, efficiently, and with global optimality. And the solve time here is also polynomial. So it's typically proportional to the bigger of either n cubed or n squared m. And this thing, n squared m, is again what showed up in both least squares and linear programming. So roughly the complexity is kind of close to those two. So how we use convex optimization, the general workflow, you formulate your problem. And this can be an iterative thing where you start with the formulation and it might not be the final one. You hope that you recognize your problem, the true problem that you wrote down, as a convex problem. But if not, maybe you do some approximations or some reformulations to get your problem kind of into a convex form. And then you use a modeling language. Typically, we will use either CVX in MATLAB or CVXPy in Python. But there are tools in Julia and R and I think others at this point. And then your modeling language basically reformulates your problem into a standard form, and it passes that to a solver that runs, gives back the solution. The modeling language transforms it back to your original form, and it says, here's the solution, and here's the optimal value. And then typically there's some tuning and iteration involved where you say, oh, actually, this solution doesn't do what I wanted it to do, which usually means that you wrote down your optimization problem in a way that didn't exactly reflect your true goals. So then you come back up to step one and you repeat. Okay, so we'll talk next lecture about convex sets and functions. Then we'll talk about formulating and solving convex optimization problems. And then over a bunch of lectures, we'll give DER examples. Yes, question.
One thing super quick, if you guys are interested a lot in optimization, I run the quantum student organization here, and we meet on Wednesdays in this room, 6 to 7, and we work on quantum optimization projects using the quantum approximate optimization analysis method, or, QBO, a lot of cool stuff that can help reduce your solve time for big problems. So there's a lot of interesting applications and totally applicable to this and, and more.
Cool. So Quantum Optimization Club meets in this room. It's like
We also
Monday
do a
nights or
lot- yeah,
something.
we do a lot of, but we have a project meeting in here on Wednesdays, 6 to
Wednesday.
7.
Wednesday, 6 to 7 in here. Okay, cool. Thank you. So yeah, we'll stop there and I will see you guys on Thursday for our last lecture before spring break.